Hi everyone, my name is Juba Ziani and I'm a postdoc at UPenn right now, and the paper I'm going to talk about today is titled Pipeline Interventions, and this is joint work with Eshwar, Arunachaleswaran, Sampath, Kannan, and Roth, who are also at Penn. So today I want to tell you about fairness in pipelines, and the reason I want to look at pipelines today is because we know that in real life, decisions by and decisions about individuals are not made in isolation. Rather, those decisions are going to be made throughout a pipeline, throughout an individual's life, and decisions at different stages of life are going to have an effect and they're going to compose with each other. So for example, if I look at the education and job market pipeline, well, in this pipeline, we can see how each decision is going to fit into the next. You can see that which preschool you're going to go to is going to affect which schools you can get into, which is going to affect which college you can get into, which is going to affect your employment opportunity, etc., etc. And the problem here is that in such pipelines, well, inequality of access to opportunities, disparities can arise at each and at every stage of such a pipeline. And then those disparities are going to compose. I know that the current opportunities that I have today are restricted by previous disparities that I faced in the past. And if I want to look at the flip side of this picture, I know that current disparities that I'm facing may have a long-term effect on what my future opportunities are going to be. And even worse, we know those disparities can arise even at very early stages. Let's say, for example, at the preschool level. The question I want to ask is then, where are we going to intervene in such a pipeline to eliminate or at least to reduce disparities? And generally, the answer to that question is not quite clear-cut. So if I look once again at the education pipeline, well, one proposition would be to intervene at the college admission level. But in practice, this might often be too late. If we believe that disparities are going to start at the preschool level, then maybe we should start having interventions earlier in this pipeline. But at the same time, if you intervene very early in the pipeline, it's going to be hard to control the downstream and to control the long-term effects of your intervention. So really what I'm trying to get to today is the fact that it might be valuable to intervene at several levels of such a pipeline rather than just myopically and rather than just at a single level. And once you start thinking about intervening at several levels of a pipeline, well, you want to understand how interventions at different stages of your pipeline are going to compose. And then you want to see how this understanding is going to inform how to optimally design intervention at several stages, several levels of such a pipeline in order to improve outcomes and to reduce disparities across groups. So our first main contribution in this paper is to provide a stylized model to think about those pipeline interventions. And I want to insist, and I'll get back to this later in this talk, that this is a very stylized model, and we just think of this as a first step, as a first model. And the goal of this model is to show and to exhibit that it is actually possible to think about such issues of fairness in pipelines in a way that is formal and algorithmic. So our model is going to be the following. We are going to have a graphical model, which is going to be comprised of several layers. And then agents are going to start in the first layer that we also call the starting layer. And this layer is going to be comprised of several starting nodes. And in this layer, well, different starting nodes are going to correspond to different starting groups or different starting subpopulations. Then agents are going to go through the subsequent layers of the pipeline sequentially. And each subsequent layer you can think of as corresponding to a stage of life. And each node on each layer you can think of as corresponding to the outcome of that stage of life. So for example, a layer could represent your college education, And different nodes on that layer could represent different education levels, different types of schools that you're going to, different majors, for example. And finally, our agents are going to end up in the final /reward layer. And so each node on this reward layer, each node I, is going to have a reward R of I. And this reward is a scalar measure of the quality of the outcome that corresponds to node I. So now I've told you that agents are going to go through layers sequentially, but I haven't told you exactly how individuals are going to go from one layer to the next. And so here, the way they're going to go from one layer to the next and progress through the graph is via stochastic transition matrices. So we're going to have stochastic transitions between layers, and those stochastic transitions are going to govern the probability of going from a node on the current layer to a node on the next layer. So for example, there's going to be a stochastic transition matrix M of t between layers t and t+1. And this transition matrix is going to be such that mt of ij is going to govern the probability that an individual in node I in layer t ends up in node j in layer t+1. And I want to note that the stochastic transition matrices can actually model disparities in access to opportunity, because you can give different groups different probabilistic paths to different reward nodes through the graph. So some groups might be advantaged and initially might have high probability path to good reward nodes, versus some other groups may only have high probability path towards lower reward nodes. And now remember that our goal in this paper is to reduce disparities by intervening on the pipeline. And so our intervention model here is going to be the following. We'll take the point of view of a centralized designer who can intervene at any and at several stages of such a pipeline. So you could think possibly of this centralized designer as the government or a government entity that cares about education. And then an intervention is going to consist into changing the stochastic transition matrices between layers in this graph. Obviously, you're not going to be able to change the transitions for free. This is going to come at a cost. So changing transitions between any two successive layers is going to be costly to you. And as the centralized designer, you will have a constraint. You will have a maximum budget that you can invest across all of the layers and all of the transitions. So our cost function is going to look like the following. So we're going to have a cost from changing from an initial transition matrix MT0 between layers t and t+1 to a new transition matrix M of t. And this cost is going to be given by C of MT0 MT. And we're going to make a few assumptions on this cost. The first assumption that we have to make is that the cost is going to be convex in MT, so in the second argument. And the reason we do so is because it's going to be necessary for us to do any kind of optimization in this problem. And second, we're going to impose an anti-Lipschitzness condition on C of MT0 MT. What that condition means informally is that as you get further away from MT of 0, you're going to increase the cost of changing from MT0 to MT. So basically, you cannot change or improve transitions for free. And I just want to point out here that the condition we use is not exactly anti-Lipschitzness. We actually use a weaker version of anti-Lipschitzness that is more widely applicable. And then, as I said before, our centralized designer has a budget, and so we have a budget constraint, which is that the sum of the costs that you spent on the transition between any two layers t and t+1 has to be less than b. And so our second contribution in this paper is to provide algorithms to find near optimal interventions for our problem. And so we have algorithms that are going to find an approximately optimal budget split across all of the layers, and an approximately optimal way to use the budget to change transitions between different layers. And our approach, which I will give more details about in the next couple slides, is going to rely on discretizing the space of distributions on each layer. So the distribution being here the probability of an agent ending up in each node of that layer. And then we're going to combine this with dynamic programming. And so the caveat here is that, well, our dynamic program is going to be efficient even if you have many, many layers. But the problem is that because of the discretization of the distribution on each layer, we're going to require our algorithms to only deal with graphs that have small and constant layer width. So the number of nodes in each layer is going to have to be small. And we provide those algorithms for two different objectives. The first one is to maximize the social welfare or the expected reward of the agents, given that you have a distribution over which population, which node agents are going to start in. And really this objective, if you think about it for a second, is the best objective that can be achieved at the level of the whole population, but it does not tell you anything about how the welfare is going to be split between different starting nodes and between different subpopulations. And so this actually might ignore minority and disadvantaged subpopulations. To address this issue, what we do is we look at the second objective, which is a max-min objective, in which we're maximizing the welfare of the worst of group. And you can think of this as being basically Pareto optimal. You can think of this as being the highest expected reward that can be achieved simultaneously for all subpopulations. And you can think of it as if you were to try to improve the welfare of any group, one group is going to get worse welfare than this maximin welfare objective. So now let me tell you a bit more about the techniques and about the dynamic program that we use to find the near optimal social welfare. And let me start with the easiest case, in which we only have two layers and we have a single transition matrix in the middle. So now if you look at this picture, on the left side, we're going to have a starting distribution over populations. So d of I is going to be the probability that an agent is going to start in node I on the starting layer in population I. And then we're going to have on the right side rewards, and R of I is going to be the reward that you get if you end up in node I in that layer, in the reward layer. And we're going to have a transition matrix M1 between the starting layer and the reward layer. So here, it's not hard to see that the social welfare is just going to be R times M1 times T. So it's just going to be a linear function of M1. Plus, so what you want to do now is you want to maximize this social welfare, so this linear function, under the constraint that the cost that you're using is less than B. But remember that the cost is convex by assumption, so we get a convex constraint. And well, we're done because we have an easy to solve convex optimization problem. So good. We know how to deal with the problem when we only have one transition. Now, what do we do when we have many layers? Well, we're going to take a dynamic programming approach. And this dynamic programming approach is going to go backwards. And it's going to start from the last layer and then build up until we get back to the first layer. So we want to start at the final layer. We want to start at the final transition matrix M of k between layers k and k plus 1. And what we want to do here is we want to solve a convex optimization problem that is similar to the one that I described to you before. We want to maximize the social welfare given that we have a starting distribution on layer k that is called DK, and that we have a reward node, that we have rewards, on the reward layer, and those rewards are given by R. So you want to solve the maximum of R times MK times DK under your budget constraints. But so what's the issue with this approach here? The issue with this approach is that we don't know what DK is here. D of k is going to depend on the early transitions, on the transitions from 1 to k, but our dynamic programming is starting from the end, from the final layer. So we don't know what D of k is. It's unknown to us at this point in the algorithm. So what are we going to do to solve this problem? Well, we don't know DK, we're just going to try to guess it. How do we try to guess DK? Well, this is where our discretization is going to come in. we are going to try all of the possible decays on layer K on an epsilon net of the probability distributions of where agents could end up between nodes 1 to W on layer K. Now the problem is that since we have a W-dimensional probability distribution, we need this net that is going to have size, an epsilon net that's going to have size of roughly of 1 over epsilon to the power of W. So we're only going to be able to deal with constant and small values of W. But now, once we've done this, well, for every decay on the net, all we have to do is to solve the optimization program that I was talking about in the previous slides. And so we're going to do this recursively until we get to the first layer. And what's going to happen here is that the net that we're using, this epsilon net, is going to make us lose epsilon in welfare at each time step. So we will get a k epsilon approximation to the social welfare if we have k transitions. In terms of computational efficiency, remember that each step requires looking at polynomially many possibilities in 1 over epsilon to the power of W because of the discretization. So we're going to need W to be constant, but as long as W is constant, we'll be fine. And you can think of W being constant as this being a coarse grouping of outcomes in each stage. And then we're only going to need to do this k times once again. So this is going to be computationally efficient as long as W is constant, but even for big values of k. And the final thing that I want to point out here is that I've talked about the dynamic program in the context of maximizing social welfare, but this can easily be extended to our maximum objective. And instead of keeping track of all of possible DTs at the start, to do that, instead of keeping track of all possible DTs at the start of layer T, we're going to keep track of slightly more fine-grained information, and we'll keep track of a distribution of T and I, which is going to depend on each starting node I. So there's going to be now in our dynamic program at every time step, there's going to be a distribution for every starting node I. And then we'll use pretty much the same approach as before. Now, remember that I told you already a couple times that we can only deal with the case when W has constant width. And here I just want to give you some quick intuition of why this is actually not something we can avoid. And I want to give you some quick intuition on our harness of approximation results. So in the paper, we will show that it's impossible to approximate the optimal minimax welfare to any constant factor in the general case. And the way you can do that is via a reduction to vertex cover. So start with a graph G. And for each edge U, V in this graph, you can build the following pipeline intervention problem that I have on this slide. So basically what you want to do here is you take the edge UV, and each edge UV is going to correspond to a single starting node in the starting layer of our pipeline intervention problem. And then in our pipeline intervention problems, we're going to have 2 reward nodes. We're going to have the good one that gives you a reward of 1, and the bad one that gives you a reward of 0. Now, in the pipeline intervention problem that we construct, there is going to be one path P of U that goes through the graph for every node U in the original graph. So for example, remember that there is a vertex in the starting node, in the starting layer of our pipeline intervention problem, U of V, for every edge UV in the original problem, in the original graph. And so there's going to be here 2 paths that are going to go from UV to the final layer. There's going to be a path PU, and there's going to be a path P of V. So there's going to be a path PU corresponding to vertex U, and there's going to be a path P of V corresponding to vertex V. And then you're going to transition from UV to each of those 2 paths with probability 1/2. So now also note that if I had another edge, say UW, in the original graph that has U as a vertex, well, it will share the same path PU as the starting vertex UV. And just a quick note, so forget about the x's that we have on this graph. Those x's are just dummy nodes that we introduce to make sure that we actually have a probability distribution that sums to 1 for each transition matrix, but they're not very important. And now here, the idea is going to be that the most efficient thing to do if you want to optimize the maximin welfare in this problem is to use as few paths as possible that are going to the reward node 1. But you also don't want to ignore any starting vertex. You want to have a path that's going to 1 for each edge. If you have a starting edge, if you have a starting vertex UV that goes mostly to 0, that takes a path that mostly goes to 0, then basically this starting population, this starting UV, is getting a low welfare, and so the minimax welfare is going to be bad. But remember that each path just corresponds to a node in the original graph. And basically using as few paths as possible is going to be equivalent to using as few vertices as possible in the original graph, in the original vertex cover problem. And so that's the general intuition of the reduction between vertex cover and our pipeline intervention problem. Finally, I want to point out in this talk that we have some price of fairness results. And in this paper, we define the price of fairness as the optimal social welfare that you can get in our pipeline intervention problem, divided by the social welfare of a maximin solution. And we're going to characterize the price of fairness in a very simple case in which the costs are going to be linear. And so basically the cost for changing a transition by 1 is going to be exactly 1. And in this case, we're going to be able to give tight bounds on the price of fairness. And the expressions themselves are not too important. But what I really want to point out here is that if you look at the price of fairness, this price of fairness is first not going to depend on K, the length of the graph. It's only going to depend on the width, W, and the budget. Second, as the width is going to get bigger and bigger, it's obviously going to be harder and harder to give good welfare to everyone, to every starting population. And so the price of fairness is going to worsen as W is getting bigger. And finally, as B is also getting bigger, it's going to be easier and easier to get the price of fairness close to 1 and to improve the price of fairness. And if you have large enough budget, if you have a lot of budget, you can basically ensure that everyone is going to have a path that goes to the highest reward node with probability 1. And so the maximin solution and the optimal solution are going to be the same thing, and the price of fairness is going to be 1. So I want to conclude this talk on some remarks about our model and some future directions. So once again, I want to insist here that we're not solving all the questions, that rather we're still trying to only provide a first step and a stylized model to show that we can think about those problems theoretically and formally. But in practice, there are many important future directions. And some of those directions are that, first, if you intervene early in the pipeline, it might change transitions not only in that layer, in the first layer, but also later in the pipeline and later stages. Also in practice, we know that transitions between beyond the transition from layer 1 to layer 2 can be different for different populations. So even if you have two starting populations that end up in the same node in layer 2, they might still face different transitions at that point. And so it'd be nice to look at this in future work. I also want to point out that in practice, transitions may not be stochastic, but they may involve strategic elements. Decisions don't just happen to them. Agents are also going to make choices, and they're also going to make decisions. Also, our model is acyclic and does not take feedback loops into account, so it'd be very nice in future work to be able to take this feedback loop into account. Our reward model is simplified. So basically, our reward model is such that the reward is scalar and everyone has the same reward on the same node. So everyone wants the same outcomes. But in practice, in real life, different agents may want different outcomes, have different objectives. And it will also be very interesting to see what happens if we have we don't have a centralized designer, we have different entities that could intervene at different stages. And those are only some of the questions. There are many questions that we can ask for fairness in pipeline interventions. Once again, this is just a first step to show that we can think about those issues, and we hope that this paper is going to inspire a lot of important and interesting future work. And that's all I wanted to talk about today, so thank you very much for listening.